Okay, now this is our class 2 on the module for crystallography. So I think in the last class we have studied about various types of solids, that is crystalline, non-crystalline, then water polycrystalline materials, single crystals, etc. Then we have learned about lattice parameters, etc. So now today we will learn about type of lattices. Actually there are two-dimensional and three-dimensional lattices. Now the four crystal systems of two-dimensional space are oblique, rectangular, square and hexagonal. So in two-dimensional lattice system we have got four crystal systems and they are given below. That is, the first one is given the name oblique. Then rectangular. Rectangular is of two types. One is rectangular primitive and the other one is rectangular centered. Then the other one is square and the last one is hexagonal. So each of these configurations have a set of lattice parameters, that is a, the value for a, b, gamma, etc. What is a and b? They are actually lattice vectors. And what is gamma? It is actually the angle between the lattice vectors, and it is called by the name interfacial angles, right? So these lattice vectors along with interfacial angles is called by the name lattice parameters. All these things we have already studied or we have already discussed in the last class. So in two-dimensional lattice we have got four crystal systems, which are they oblique, rectangular, square, hexagonal, and in that rectangular is of two types. One is primitive and the other is centered. Then you have to write their lattice parameters. That is, for oblique it is a not equal to b but gamma not equal to 90, and similarly you have to specify those lattice parameters for each of these four crystal systems. Similarly, you have three-dimensional lattice. There you have got seven crystal systems, which are they? This is very important: cubic, tetragonal, orthorhombic, rhombohedral or trigonal, then hexagonal, monoclinic, triclinic. These are the lattice parameters. For cubic, all the lattice vectors a, b and c, all of them are equal. But what about tetragonal? C is not equal to. Similarly, the interfacial angles alpha, beta, gamma, everything is equal to 90 for cubic, whereas it's for cubic, tetragonal and orthorhombic, whereas for rhombohedral alpha and beta are the same but gamma is not equal to 90. Similarly, you have to study the name of these seven crystal systems along with these lattice parameters. That is, this one is are the lattice vectors, these are the interfacial angles, so they are together called by the name lattice parameters. See the heading, lattice parameters. So you have to study this table very well. Then these are actually the rough sketch of these seven crystal systems. This you can just go through. Then lattice directions and planes. Direction of line in a lattice is defined by certain indices assigned to that line. Now what happens if the line passes through the origin? Then the indices are determined. How? By taking a point on this line, and then we find the projections of the vector drawn from the origin to that point on the crystallographic axis. Now let us name those projections as u, v and w. So u, v and w will naturally represent the coordinates of that point. These coordinates we can simplify to get a small set of integers which can be enclosed in square brackets. Okay, and that will represent the indices of the line. So these are nothing but Miller indices. We will be dealing with that very soon in the coming sessions. Okay. So here they have given an example. As an example, in order to determine the indices of the direction OQ in a cubic crystal, see the figure, in order to represent or in order to write the indices of that particular direction OQ, what we have to do is that we may take either a point, that is P, its coordinates are half, 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 or it can take it as Q111 on this line. So we take a point on this line OQ, and then the direction of OQ is represented as 111 within square brackets. Now the same will be the indices of any other direction which is drawn parallel to OQ. This is because the origin is shifted in such a way that orientation of axis remains unchanged. That is, the indices of the line OQ will be the same as the indices of another line which is taken parallel to OQ. Why? Because when you do this, the orientation of axis remains unchanged. So the indices also will remain unchanged. Now let us see what happens if the direction is taken perpendicular to the axis. In such cases, the index corresponding to that axis will be 0. A direction having projections on negative side of the axis, we have positive and negative axis, and if the projection is on negative side, what will you do? You will put a bar sign over the indices like this. If it is, the indices are like this, if this actually represents on the positive side, if it is negative, you just put a bar. Okay, that is the only difference. That is if the projection is made on the negative side. Now the angle theta between the crystallographic directions HKL and H dash K dash L dash is given by cos theta equal to hh dash plus kk dash plus ll dash divided by s square plus k square plus l square, the root of that, into root of h dash square plus k dash square plus l dash square. Now this is Miller indices. Miller indices is very important, so you have to study it very well. It is nothing but a scheme to represent the orientation, that is how it rotates, orientation of a plane in a lattice. It was discovered by a British crystallographer named Miller, hence the name Miller indices. So it's nothing but Miller indices is a scheme to represent the orientation of planes in a lattice. Now, these are the various steps involved in determining Miller indices. First one, what you have to do is, you have to find the intercept of the plane on the crystallographic axis. Then you have to take the reciprocal of those intercepts, and finally you have to remove the fractions, if any, and then enclose the numbers that's obtained in parentheses. Okay, now if a plane, just note a point, if any plane is parallel to an axis, then its intercept with that axis will be taken as infinity. So this is a figure that's given to you, and you are asked to find the Miller indices of this plane. Okay, that is a plane ABC is given, and the intercepts that this plane ABC is making on the crystallographic axis is given as 1, 2, 1. Then how will you find Miller indices? What was the first step? Find the intercept of the plane on the crystallographic axis. In the question, they have given that intercepts as 1, 2, 1. So you just write the intercepts as 1, 2, 1. Now what was the second step? Just take the reciprocal. Reciprocal of 1 is 1 itself. What is reciprocal of 2? 1 by 2. Then 1 is kept as such. What was the third step? You have to remove the fractions, if any. Yes, there was a fraction involved, half. How will you remove that? Just multiply with the 2. Okay, so what will be the answer? It will be 1. So since you are multiplying with 2, we have to multiply this 1 also with the 2 and this 1 also with the 2. So what will be the answer? Here it will become 2, because 1 into 2 is 2. This one, as I already told, this one also you have to multiply with the 2. So it will be 2, 1, 2. And finally you have to enclose those numbers in parentheses. That is, you have to write this as 2, 1, 2. You should not separate it with commas. Don't put commas in between. So this is of the form, in general, Miller indices is of the form HKL. So here your answer is written as 2, 1, 2. Don't put commas in between. Okay. So you got the intercepts as 1, 2, 1. You took the reciprocal, so it became like this. You have to remove the fraction. So in order to remove this fraction half, you multiplied it with the 2. So you have to multiply this one also with the 2. So it will become 2. On multiplying half with the 2, it will be 1, and multiplying 1 with the 2, it will be 2. So 2, 1, 2. This is how you get the Miller indices. Okay. Now you will be asked to define Miller indices, and you will be asked to write the steps involved in determining the Miller indices, and sometimes they will give the intercepts and you will be asked to find the Miller indices. Okay, so this is a possible question. So study this Miller indices part very well. Okay, it may be noted that another plane, suppose that you have another plane in the figure DEF, which is parallel to the plane that we have discussed now, ABC, and suppose that it lies completely inside the lattice and it's making the intercepts half, 1, half. Then what will be the Miller indices? Just take the reciprocal. So here they have given the intercepts as half, 1, half. So take the reciprocal. So it will be 2, half, 2. To remove the fraction, what you have to do, you have to multiply with it 2. So this will become so taking the reciprocal, no, this will be 1 itself. Okay, multiply with the so there is no fractions involved, so there is no need of multiplying. So what will be your Miller indices? It will be 2 1 2, just the same as that we got before. So hence it may be concluded that parallel planes will have same Miller indices. Okay, now next session, if the plane intercepts an axis on negative side, which we have already discussed, what we have to do, we have to just put a bar on the top of those figures HK. Now intercepts of a plane passing through the origin cannot be determined. How will you find the intercepts of a plane passing through the origin? In such cases, we have to consider another plane parallel to the given plane and then determine it Miller indices. Okay. Then another possibility is that you have to shift the origin from the plane to some other point without changing the orientation of axis. That is another way to find the Miller indices of a plane passing through the origin. Miller indices of a plane are two parallel planes. Miller indices of two parallel planes will be always equal, as I already said. Now the last session is interplanar spacing. Interplanar spacing is nothing but the space between any two adjacent set of parallel atomic planes. We know that in a crystal atoms are arranged in various planes. So now the distance between any two adjacent set of parallel atomic planes will be called by the name interplanar spacing, and it is represented by small letter d. Small letter d. Okay. Now here, consider a set of parallel planes with indices HKL. Take origin on a lattice point of one such plane and draw crystallographic axis ABC. This is you just can read. Now consider another similar plane adjacent to this plane. Now let the Miller indices be HKL. Let the length of the intercepts on ABC, the crystallographic axis, are A by H, B by H and C by L respectively. Now, if we draw a normal from the origin to the second plane, the length of the normal will represent the interplanar spacing D. So, from figure, this is a figure that is given. So, just draw the figure. It follows that what is the interplanar spacing D? It is equal to OP. It is well clear, or the distance between any two adjacent set of parallel atomic planes. That D can also be written in terms of this crystallographic axis and interfacial angles alpha, beta, gamma. How is it written? A by H cos alpha, it is again equal to B by K cos beta, again equal to C by L cos gamma, where alpha, beta, gamma represent angle between normal and the crystallographic axis ABC respectively. Now, if n cap, let n cap be a unit vector normal to the plane, then A cos alpha, B cos beta and C cos gamma can be written as how? N cap dot A vector, n cap dot B vector and n cap dot C vector respectively. So just make that substitution, and then the D value will become, how will that become? The first equation will change to n cap dot A vector by H equal to n cap dot B vector by K equal to n cap dot C vector by L. Okay, now the value of D can be determined if n cap is known. Now, suppose that you are considering an orthogonal lattice where all these vectors A, B, C point along x, y, z directions respectively. Then the equation of plane can be written as f of x, y, z equal to hx by A plus ky by B plus Lz by C equal to 1. This is definitely an equation for a plane. That is your equation 2. Now, suppose that if the surface of this plane is a constant, then del f represent a vector normal to it. So, n cap can also be written as del f by modulus of del f. So, what is del f? We have already written, it is h by a I cap plus k by b j cap plus l by c k cap. Now, what will be its modulus? Just take the square it and take its root. That is s square by a square plus k square by b square plus l square by c square's root. So, your first equation, it will reduce to, that is D is equal to in place of this n cap, just take the first term alone, that is d equal to n cap dot a vector by h. In that place, instead of n cap, you just substitute the value of n cap that we have just got, and a vector by h cap will be kept as such. See the formula. Okay, d equal to n cap dot a by h, that is n cap, the value of n cap is just substituted from the above equation, and a by h is kept as such. You have kept a I cap also there. So on simplifying, what will you get? This h by a I cap dot a by h I cap. These terms will not have any relevance. Why? Because you are dealing about I cap, because we are taking the only the first term. So this one will not have any relevance. So h by a I cap dot a by h I cap, what is its value? H and h get cancelled, a and a get cancelled, so I cap dot I cap is 1. That is why you got a 1 here. Now the denominator is kept as such. So the value of d for an orthogonal lattice is given as, its formula is 1 by root of s square by a square plus k square by b square plus l square by c square. Now from here, can you find the interplanar spacing or the formula for interplanar spacing of a cubic lattice? Yes, you can find. Why? For a cubic lattice, a equal to b equal to c. So definitely for a cubic lattice, the formula for interplanar spacing d will be equal to 1 by root of s square plus k square plus l square. See, it is given just below. Okay, since it is equal, you can take the length of the cube as a, in the case of cubic lattice d. Okay, because a equal to b equal to c, so as you can put that, let it be a itself. So naturally a will go to the top, it will come in the numerator. So the formula for interplanar spacing d for a cubic lattice will be a by root of s square plus k square plus l square. That is given here. Okay, so here in today's session, the most important part is either you will be asked to derive the interplanar spacing, the value for d. So this essay part is important, that is derive an expression for interplanar spacing, that you have to study. Then give due importance to Miller indices, the steps involved. Sometimes they will give the indices and you will be asked to find the Miller indices and like that. Okay, then they will ask this one. The three-dimensional crystal system is more important when compared to two-dimensional crystal system. So these are the main points that you have to study in today's session. Okay, thank you.